Hierarchical reasoning model. So this paper came out about a month ago, and it's a very interesting model because they claim they can do stuff that normal LLMs can't, like normal language models, with only 27 million parameters. So compared to GPT, which has, I don't know, hundreds of billions, I don't know what GPT-5 has now. 27 million is basically nothing compared to that. So the fact that it can beat these models on certain tasks, like it's not language tasks, they don't test it on language tasks, they test it on things like ArcAGI and Sudoku, more reasoning tasks rather than just language modeling tasks. And that's quite surprising. But I was initially going to make a video about this, but then there was a lot of discussion about this actually being trained on the test data, or they're kind of being like there's kind of some cheating going on in terms of how they actually train these things. And if you're curious to see all of that, go to Twitter X, it's still Twitter, and go check that out. There's a lot of discussion behind did they actually fake this or not. This is actually real, and it seems like it's somewhere in the middle where it's like it's kind of. Do they game the benchmarks? It seems like the answer is kind of, but I don't know. I'll let you make your conclusion on that. I do think there are some interesting parts to this that I think are worth talking about. So even if it is gamed a little bit, I do think there are some interesting parts that, like, it's different from a normal transformer. So I think it's worth talking about, worth digging into, and yeah, that's why I'm gonna talk, or that's why I'm talking about it now. So yeah, I'll kind of give a few opinions at the end, but I'm not gonna say, like, I don't know if this thing was over or if this thing was gamed or not. I didn't train it, so I'm not gonna give an opinion that's too strong about that. Anyways, so what's the idea? The idea is down here, and they basically say that, like, if we have some data, so we have some data X, that can be anything. Maybe our data is language, so we have our data as a set of tokens, and the task is to predict the next token. Or maybe our data is whatever, like Sudoku, so you have your Sudoku grid. Sure, that works. It has some numbers in here. And that doesn't make any sense. Whatever. I'm not drawing a 9x9 grid. 9x9. But we all know Sudoku, and you basically give it the starting puzzle and it completes it, or you give it maybe another puzzle and it completes it. Basically, give it some data X, and you want it to do some reasoning task. So how do you normally do this with a large language model? What you normally do is you say, all right, so we got a bunch of text or a bunch of tokens here, and I throw my tokens into my large language model, and it produces another token, and it does this autoregressively. And what you can do is you can just say, well, I'm going to ask a question, I'm going to get an answer. Or what you can do is you can do this test time compute thing, which is very much where a lot of the research is right now, where you basically say, ponder this answer, do some step-by-step reasoning, and then actually answer the question. But the LLM itself isn't really, like, it's not really doing this. They argue it's not really doing this reasoning. Internally, it's kind of doing it externally. It's okay. It's not awesome. It's okay. It's limiting. But what if you actually train this model to reason from the beginning? So instead of just having a language model where it produces a token, what if you have this model actually reason internally from the beginning? So instead of just doing a bunch of forward passes, have it reason in some way. So that's kind of the basis of their model here. So they compose their model of two parts. They basically have, you can think of this as just a recurrent neural network. So for a normal recurrent neural network, what you do is you have your hidden state here, and you have your model, and your model will take in the hidden state. It'll take in some data at time t, and it'll update itself. And you normally have a recurrent neural network go over time. What we're going to do is we're going to have a recurrent neural network just kind of update itself. So just you can think of this as it kind of pondering on this hidden state in some way. So if you just have this, it'll basically take in the hidden state, output another hidden state at time t minus 1, and it'll put that back in, and it does this over and over and over and over again until you say that's enough and I want an output. So you can think of this as, I don't know, the initial hidden state is maybe the Sudoku puzzle I wanted to solve. It then outputs, it then iteratively refines the Sudoku puzzle outputs, however I define that, and it eventually ends up at a solution, and I observe that solution. So maybe this is the 9x9 grid, it iteratively updates that, and then I observe that. Or maybe this is some ArcAGI puzzle, or maybe this could be some text, where this is the input text, it ponders on, it outputs some hidden state, maybe that's some, you can think of this as basically like one of the layers in a transformer, except we're doing this iteratively with a recurrent neural network. So maybe it could output, instead of just outputting the text token immediately using one forward pass, you would send that token back through and do this iterative refinement on that token. So that's the idea, this iterative refinement. However, if you just do this with one recurrent neural network, just one hidden state, it's okay, it's kind of been done before, but the idea is, what if we have two hidden states, one that's updating slow and one that's updating fast? So this is the basis of their entire algorithm. This is basically it, and then they do a lot of other things on top of it. So this is their entire model, and the idea is you have your data here, so that could be your text data where you want to predict the next token here. That could be your Sudoku puzzle where you want to predict the final, like the solution to the Sudoku puzzle, or it could be like ArcAGI puzzle, something like that. Some input data, and you want this to be solved in some way. Your input, maybe the input data is some puzzle, you want it to be solved. And to do that, you're going to do this refining with two pieces. You have one piece, well, I guess you have 4 pieces. The first piece is you need to take your input data, you project it using FI, and this is just embedding it into some useful way to work with the data. You can't just pass a Sudoku puzzle into a model and have it work on that. You need to embed it in some way. Maybe you tokenize it. Like for example, this is tokenizing text or something like that. So you need some input module, or some input layer. Once you have your input, we call that X. You then have this iterative refinement I talked about earlier with this FL. And this is going to be our fast moving model, and they call it the lower level model. Basically what it does is it operates on 3 things. It takes in the hidden state, so its hidden state. It takes in the input data at every time step, and it also takes in this higher state. And we'll talk about this in a second. But basically what it does is it does what we said above, where it takes in the hidden state, it takes in the input data, and it iteratively updates itself. So it'll output this first refinement on the hidden state. So it updates the hidden state once. It then sends the hidden state back into itself, and it does this over and over again. And what we do is we do this t times, so whatever value you want to pick for that. And then what we do is we have this higher level model, which takes in whatever this lower level model produced after t steps, and the hidden state for the higher level model, so the slow moving model, and it'll update itself. Once this is updated, we then go back to the lower level model. We update the lower level model t times. So the lower level model does t passes on this hidden state here. And then we do another high level model, slow model update, again on this state here, and this state here. So basically what you have is you have 2 recurrent neural networks that you're working on. One recurrent neural network updates itself over and over and over again every step. And another recurrent neural network updates itself just every t steps on this lower level model. So the idea is this lower level model can kind of move around the space, converge into some spot in the space of some whatever this higher level model needs, and the higher level model observes that. It takes that information, updates its hidden state with that information, and then the lower level model can go back, update itself a bunch, converge to some stable state, the higher level model observes that, and it does this over and over again. You can think of this as just like running around the space, and this is actually like creating an average of the useful information that the lower level model accumulates. So maybe the lower level model is like trying different things or something like that. That's the intuition behind it. How does it actually work? Like, what does it actually learn in practice? It's a different story. But once you have your higher level model updated sufficient number of times, so they say n different times, you then pass that through an output layer, so normal output projection, like an unembedded layer for your LLM, and this gives you your final output prediction. So yeah, I mean, it's not super complicated. It's pretty intuitive. It's basically just you have one model that's updating a lot, and you have another model that's observing the model that's updating a lot periodically, and that way you get this signal is a lot more noisy. This signal is a lot less noisy, and you use the less noisy signal to do your output prediction. So they show that right here. In mathematical terms, or using mathematical notation, they have the lower level model is equal to, or the lower level hidden state is equal to the lower level model on the current hidden state of the lower level model, of the higher level model, and the current input. So it basically needs to know maybe it needs to know what information does the higher level model need, what information, like what's the starting point, X that I'm starting at, and what state is the current lower level hidden state at. The higher level model here updates itself every t steps, and it updates itself by this here, where it basically updates itself using the past higher level model hidden state, and the lower level model hidden state. So it's kind of like an average of what their lower level model sees. So the way they actually, like, what are these models here? This model and this model here are transformer layers, or just simple transformer layers, and the way they combine the inputs is just by adding them. So since we're not actually doing a prediction until the end, all these hidden states here are of the same shape. So that's what these models actually are. So one transformer that's moving very fast, updating very fast, and one transformer that kind of averages those. So yeah, moving on from there, we'll get to this graph at the end. There's a lot of good information here. So one thing they note, or rather like the intuition behind this, is again, the lower level model basically has a stable convergence to a local equilibrium. This equilibrium depends on the high level state supplied during that cycle, so it knows, so it's kind of conditioning where it's going to converge to using the high level hidden state. And after completing t steps, the H module incorporates the higher level module, incorporates the submodule, the subcomputations outcome. So the final hidden state is EL. So the idea is it'll converge. The high level hidden state, or the high level model, will observe where it converged, and then the low level model, since it has information of the high level model, it'll go converge to a new location, and you have this this repeats over and over again. So that's the idea there. Approximate gradient. So with recurrent neural networks, they are annoying to train because of backpropagation through time. So you have your rollout here of a bunch of recurrent neural network calls here. And what you have to do is you have to do this really, like, first off, this is really slow because you have to iterate over time. So time, but to update the model, you have to iterate over time backward. So it's slow going both forward and backward. For this is one of the problems with recurrent neural networks. So it's annoying to deal with this. And the way they deal with it is by basically not dealing with it. Or they basically say, they use this one paper, which I wrote down here, on training implicit models, which basically assumes that if your model converges to a high-level fixed, so if your model converges to a fixed point, like defined here. Basically, if your model here takes in the current input and it outputs the same thing, it's at a fixed point. And if it reaches, if it does indeed converge to a fixed point, you can approximate the gradient using this one-step approach. So they define all this here. But all this is from the On Training Implicit Models paper. And if I draw out the path this actually takes, so normally you would do backpropagation all the way back here to update your high-level model. You would do backpropagation along this path to update your low-level model, and then you would do backpropagation along all of these paths to update your input layer. And that sucks to do. So that's slow. It's memory intensive. What this one-step approach does is it says, well, we'll just approximate it with the final step. So you do backpropagation along this path here, along the orange path, and that can be good enough, assuming all the assumptions you made are correct. They make a lot of assumptions. So does that actually work in practice? Probably not. It's not as good as if you did the full gradient computation, but it's good enough. And they show here how to do that. So this is the code that they have. This is the HRM module. Basically, for the HRM module, you do this low level or high level iteration here without any gradients. And what you do is you compute the actual gradients, assuming it has indeed reached a fixed point. You do the high level gradients just by using one step. So the way you do that is just by passing this through you pass the final hidden state through the low level model and the high level model one more time. Again, this is kind of hand wavy. It's like it works if you do have convergence to a fixed point here, Z star. Does it actually do that? It doesn't actually look like it does. So I don't know. This gradient may be a little more noisy than the actual gradient. Anyways, if you are curious more about this and if it actually works, there's On Training Implicit Models, that paper, which actually explains this better. So another interesting thing is deep supervision. So I don't actually think that this is kind of interesting. This gradient part, what I think is kind of cool. Like they have this kind of early stopping thing. So the way they do that is they start with deep supervision. And the reason I think this works well is because they add deep supervision. So if your model just stopped at the end and this is the computation you actually did, I don't think it would work that well. But what they do is they say, well, what if we do an HRM model and we do that m different times? So instead of just doing one forward pass, we do m different forward passes, where the previous forward pass uses the state of the next forward pass uses the state of the previous forward pass. So deep supervision, that's what they say here. So I have some diagrams. So normally what you would do is you would take in your hidden states here, your input, and you get out your hidden states updated. This would be updated n times t times. This would be updated t times, n times. And this would be updated, and this is your output observation here, where your loss is right here. So what they do is they say, what if we do that multiple times? So what you're going to do is, if I just take this piece here, this is one HRM call. However, what we can do is we can say, well, what if we do this again? So we take these inputs, we basically start off the model wherever these hidden states were, but we detach it. So we detach these so that the gradient isn't annoying and it doesn't have to flow all the way through however many HRM model calls we do. So yeah, you detach the gradients for your hidden states here. And basically what you're doing is you're doing a whole nother HRM pass just on wherever these hidden states landed. So your model kind of goes around the space, it lands in some spot, you compute the loss for that. So you have like your space, it lands in some spot, you compute the loss for that, and you're like, maybe that wasn't good enough. So your HRM model then refines itself by doing another HRM model call So it'll maybe converge to another point here. And you do that multiple times so that it learns better. More iterations, more test time compute, it should only do better. And the reason I think that this actually allows the model to work rather than just one forward pass, or rather than just one pass, is because you kind of get a semi back propagation through time. It's like you get this, you kind of get this. So if we have two calls, if we just did a full back propagation through time, it would be 2tn different calls we're making to our hidden states, and you do back propagation through time over all these hidden states. If you just do one HRM call, then you would do back propagation on just this path here, which is, the signal is not that high. But if you do it again, then you get 2 gradient passes here. And if you do that m different times, you get m different updates from your back propagation through time, which would normally have m times n times t updates. So I think that's why it works as opposed to if you just did this one time. But anyways, what they say is you can do this m different times instead of just doing it once. So that's what they say here. They say HRM of these are your hidden states. This is your input. Gives you new hidden states. You then compute the loss on the mth output, and you do an optimizer step on there. Then what you do is you pass this back into your HRM model until you do this however many times you define it as. So you get m different loss outputs to help guide the model to the right spot, to help optimize the model instead of just having one loss that is a very sparse signal, because you don't do full back propagation through time. So yeah, that's deep supervision. That's one thing they add. Now, an interesting thing that you can do with deep supervision is you can do early stopping. So I do this m times. I call the HRM model m different times. And note that the HRM model is this entire thing here. So it's a lot of different hidden state calls that we're doing. But I do this m different times. Now, if the hidden states converge, and I pass them through the HRM model again, and the HRM model doesn't really do anything to these hidden states here, then there's no reason for me to really there's no reason for me to do more passes. So let's say I have m equal to, say, I don't know, 10. And I have my space here. Maybe it converges. So it iterates very, very fast. For the first call, it finds a good spot. It then iterates slightly faster for the second call, for the second HRM call, and then for the third, fourth, fifth, sixth, it stays around this area. It's probably good enough if we just take the output for the second call, because doing more calls doesn't really do anything to the hidden states. And what they do is they basically use this Q-learning algorithm to have the model stop itself. So basically, if the model output, if the model by the second HRM iteration already gives us the right output, then there's no reason to do more iterations. So what they do is they train the model to stop itself by basically having it, I don't know, quote, say, yeah, this prediction is good enough. So it learns to stop itself early to say this prediction is good enough, and it gives you the output prediction. So how do we do that? So looking at this over m different calls, for the mth call, we take the slow-moving high-level hidden state here. So that's this here. We have a projection here, which projects it to 2 logit values, which are then passed through a sigmoid function. And what these represent is it represents the action of halt and the action of continue. So do I stop myself now? Is this hidden state good enough? Is this sufficient for me to make a good prediction? Or do I continue? Do I still need to iterate on the hidden states I currently have? So how do you train it? So the way they do training is instead of just iterating m different times, so instead of just iterating m times, what you would normally do if you didn't have this, now that our model is making a prediction of halt or continue, which are both binary scores between 0 and 1, because we pass them through a sigmoid function, if halt is greater than continue, if the score for halt is greater than the score for continue, we stop. But if the score for halt is not greater than continue, then we continue. And we continue doing HRM passes until we either reach a state where the score for halt is greater than the score for continue, or we reach m different passes, so that the model doesn't continue indefinitely. Now, how do we train this? So if the model predicts halt, then intuitively, the loss will be 1 if the model got the right prediction, and it'll be 0 if the model did not get the right prediction. So should you have halted, or should you not have halted? The assumption here is the model will do better if it continues. So that's kind of the implicit assumption here. But basically, it's if you predict halt, did you get the right prediction? If you predicted the right prediction, good job. This state has a score of 1. If you did not, this state has a score of 0. You should not have halted. So yeah, this is the score we're going to train on here. And if it continues, then there's kind of two different states we look at. There's the first state, which is easy. It's if the model predicts continue, but it already reached this hard set limit we had. Maybe we set this limit to like 10 different times. If the model iterates for too long, we want to stop it eventually. So what we do is we kind of carry over the Q value here, and we say the score is just going to be equivalent to this halt Q value here. So you basically carry over the halt score acting like it did halt. Basically saying the Q value of this state is equal to halting halting, yeah. So just carrying over that value. Now, if that's not the case, if it does predict continue somewhere in the middle of this chain, then what we do is we say this continue value is going to be, so the value we're training on, what we want the model to learn, is going to be equal to the max of the score for halt and the score for continue. Intuitively, this means that if it predicts continue, should it have predicted halt? So if it predicts continue and the continue score is higher, then that's fine. Not a big deal. But if it predicts continue and the key value for halt is higher, then it basically updates it in the direction of, it updates it such that it's more likely to make a prediction for halt. Like the expected value of halt will be increased, will be higher than continue for this state here. So that's how we train it. We train it off these scores here. Basically, just BCE, because we have a sigmoid activation. So kind of what this means is if you have your rollout here, if we were to stop, like if we have a rollout and we do, say, m equals 5 passes, and you do this, you do this 5 different times, stopping here is just as good as stopping here if the prediction was correct here. But stopping here, the value for continue should be higher. So that's what we're training it to do. If it has a value of 0 here, the value of continue will be higher, the expected value for that. While if you, basically it's this early stopping, it's early stopping where the value of future states, if it's correct, is equivalent to the value of the current state, if said prediction is correct. So kind of what we train it to learn. And what you can do is basically you get this early stopping, which is nice during training because you don't have to do complete rollouts every time, assuming it doesn't reach the end every single time. So this basically adds holes in your batching, and you can fix that by basically, once it predicts halt, you just replace it with a new piece of data, starting from the initialized hidden states. So this is kind of, I guess this is kind of a messy diagram, but basically if we have a batch size of 3, and this is iterating over m passes through time, so in this case this would be m is equal to 4 different HRM passes. So on the first pass, if the first batch and the second batch, so we update our hidden states here, and if the first batch and the second batch predicted continue, or if the first batch and third batch predicted continue, but the second batch predicted halt, we would then replace the data for the second batch with new data, and then you just simply replace it, but continue with batch 1 and batch 3. So basically, instead of just continuing, you can have infinite, or you can have this, you get no holes in your data pipeline if you just simply replace any halt predictions with new data, initialized from initial hidden states. So that is their Q-learning thing. I think they call that ACT, yeah, right here. Adaptive computation time. Yeah, essentially training the model to predict when to stop itself. Now, one thing I am curious about is if they make these assumptions, they kind of make it twice, where they kind of claim that this will happen. This is intuitively it's going to happen, and they make the assumption here. It's that these things converge to a fixed point. And if they converge to a fixed point, why not just use that convergence via some threshold instead of this Q-learning thing? I don't know, just a thought. I'm curious if this is needed, or if just saying, well, it converged within some radius, it's good enough. I'm curious if, because the model doesn't actually learn to stop itself whenever it converges, which is interesting. So, yeah, just a thought. If the assumption is that it'll converge, then why not? If that's the assumption you're making for this model, then why not stop itself whenever it does? So, like if the idea is to stop whenever it's done thinking, and they define done thinking as being at a fixed point, why not just stop early when the change in the hidden state is small? And again, they make this assumption for the gradients. So that is the Q-learning part, where they teach it to stop itself. So the final loss is the BCE loss for this Q-learning objective to allow it to stop itself early, plus the normal loss, whatever this may be for whatever task you're doing. So let's go over to this graph. That's kind of the entire model, and they have some interesting things that come from this. So what they show here are comparisons right here. They have comparisons of forward residuals and BCA trajectories. So looking at the forward residuals here, that's this upper level graph. These upper level graphs here for forward residuals. If we look at a recurrent neural network, basically it converges really fast, and that's bad because you don't get, there's no reason to do more passes. You don't really get this thinking that they want, or so-called thinking that they want. If it converges really fast, there's no reason to do more passes. You want it to be slow and converge slow, to have a steady and slow convergence rather than a really fast convergence to whatever point. They show here that a normal deep neural network, so like a normal transformer, does diverge. So if you look at the residuals for a transformer, you get exploding, the values explode. If you just look at the last layer of a transformer model, the last layer output is crazy compared to like the initial output. So you have divergence for a deep neural network. And again, this is similar to if you just had a recurrent neural network as all your layers, or if you have actual transformer layers. And here they say that their method has this slower convergence, but it has these oscillations. So this is the fast-moving model, and the fast-moving model is updated every 10 steps in this case, and the slow-moving model is updated every step. They say the fast-moving model updates whenever the slow-moving model converges, and that's kind of true. So you can see the slow model or the fast model kind of converges, but it actually gets updated here. And then it kind of converges, and then it doesn't converge and it gets updated here. So it's not exactly one-to-one, but I can see what they're kind of talking about, that the low-level model kind of converges to a point, and the high-level model observes that, except the low-level model converges to a point, and then it doesn't, and then it converges to another point, and the high-level model updates on an offset of that. So that's kind of true. But it is interesting that you do see this oscillatory behavior for the residuals in the low-level model, and the high-level model updates. So that could also mean that it does converge, so I guess it is stable. But yeah, it converges slower than a normal RNN. So one can argue that it's better because it has slower convergence, so it's a more stable update. You can see that here with the high-level model, it converges a lot slower. So one can argue that it is a lot more stable. So the next thing are these PCA trajectories. We can see here for a normal RNN, it converges to a point, and then it kind of converges to another point, and then it just jumps around there. So you can see that in this graph here, converges to a point, and then it converges to another point. It kind of converges here. So basically, their argument is this is kind of bad. This is useless computation here. It already converged. You want slow convergence, not this really fast convergence. Here, this is for the transformer. Obviously, it diverges, so it's as you would expect. Here, for the principal components, you can see that it kind of it's the same behavior as up here. It converges to a point. I don't know where it starts. Right here, converges, and then it converges to another point, and over again, instead of it just converging to one point where the high-level model is observing this kind of chaotic behavior from the lower-level model. So yeah, I do think that's interesting. I think this is kind of cool. And if it actually works in practice, that would be really cool. So now for the actual, so they basically claim that they do really, really well. Let me find, so on ArcAGI, on Sudoku Hard, on maze navigation, they claim they do really well for such a small model. They beat a lot of the larger models. So let me see where these results are. Yeah, I think this is it. No, this is ACT. Yeah, here they basically show that the model does actually, it does actually work, where it does limit itself, it does stop itself early. I guess that's down here. No, results. Oh. Is it? Well, they do claim that they do really well. So yeah, here it is. Okay, I know the graphs are here that they claim they do really well. So yeah, they claim that no model can do this maze solving task, literally zeros, and they claim they can. For Sudoku Extreme, they claim they can, and no other model can. For ArcAGI, the other models can kind of do it, but not nearly as well as HRM. And again, they show that here. If we go down, they do a ton of data augmentation, and that could be why they do so well on this. So I have highlighted that right here. For example, for ArcAGI, they say they start with all input-output example pairs in the training evaluation sets. It's augmented by applying a bunch of augmentations. Each task example is prepended with a learnable special token that represents the puzzle it belongs to. So one thing, they claim it's kind of cheating because of this learnable special token. You add all these augmentations. So in a way, maybe you're kind of training on the test set even in an implicit way. But yeah, there's kind of been talk about that. But I won't go into that too far. Basically, they claim they do really well. Do they do this well? No, they don't do as well. They don't do this well. It's not It's not this massive of a gap, but I do think that the results they have are interesting. I do think it's kind of cool. I need to, before I make a conclusion about whether I don't want to make a conclusion about whether they fake this or not, because I didn't write the paper, so I don't actually know. But they are very surprising, the results, for using a transformer that does iterate upon itself. So yeah, the results are a little sus. If you're curious to see more discussions about the results being sus, there is a lot of discussion about that. But yeah, they claim it does pretty well. Aside from the results, I think this model is actually interesting. Now they do also go into a lot of like this brain stuff, and I'm not even going to talk about that. This is a transformer. It's not the brain. So I'm not even going to talk about this brain stuff that I mean, if you look at this, wow, look at this. This looks very similar to this. It's almost the same. I would say they are basically identical, the transformer and the brain. Yeah, no, that's not a thing. So that also makes it a little bit more sus that they had to bring in this brain stuff just to make their model look a little bit better. But I do think that the model they have is kind of cool. So I wanted to talk about that. Yeah, hierarchical reasoning model. Yeah, let me know what y'all think about this, or if there's anything, like if there's any interesting discussions y'all have found. I'm curious to see if this, I'm pretty sure, like from the discussion I've seen, it's not as good as they actually say it is. But I am curious to see if there is actually anything cool that comes out of this that for reasoning stuff like ArcAGI. Anyways, it's enough from me on that hierarchical reasoning model. Hope this explained the architecture. Found that part useful. Maybe not the result part, but yeah, that's the paper.